In this video, we'll look at sums of infinite series. We'll start by revising what a finite series is. A finite series is the sum of all the terms of a finite sequence. And an example of a finite sequence is something like this. We'll have 2k plus 1, with k going from 1 to 10. And that's equal to, well, it starts with 3, then it goes 5, 7, and so on, up to 21. So an example of a finite series is just all of these things added together. So that's 3 plus 5 plus 7 plus all the way up to 21. To do this, we write sigma, which means the sum of, and then the rule for the kth term. So that's 2k plus 1. And then we have to write from where k starts from, and where it goes to. So that's from k equals 1 up to k equals 10. In this case, the sum of this series is 120. An infinite series is the sum of all the terms of an infinite sequence. So I'll give you an example of an infinite sequence here. We could have 1 over 2 to the k, from k equals 1 to infinity. And that is a half, a quarter, an eighth, and so on. So the series that goes with this sequence would be a half, plus a quarter, plus an eighth, and so on. And again, we can use sigma notation to write this. We put down sigma, like we did before, write down the rule for the kth term, so that's 1 over 2 to the k, and this time k starts at 1 and goes on forever, so I'll put an infinity on top of the sigma. Now what could we mean by the sum of this series? We'll add up the first few terms and see what happens. So our series was a half, plus a quarter, plus an eighth. I'll put down a few more terms this time. It's 1/16, 1 over 32, and so on. If I add up the first two terms, I get 3/4. If I add up the first three terms, I get 7/8. If I add up the first four terms, I get 15 over 16. And if I add up the first five terms, I get 31 over 32. The sums of these first few terms are called partial sums. We say the first partial sum is just the first term on its own. The second partial sum is the sum of the first two terms, so in this case 3/4. The third partial sum is the sum of the first three terms, so in this case 7/8, and so on. If we write down the partial sums, so that's a half, 3/4, 7/8, 15/16, and so on, we can see that they form the beginning of an infinite sequence. The nth term of this sequence is the nth partial sum. And if you look at the sequence, you can see that it gets closer and closer to 1, so it has limit 1. So that means as you add on more terms of this series, it gets closer and closer to 1. So it would make sense to say that this series has sum 1. So the series 1 over 2k, or k equals 1 to infinity, which is this, equals 1. If we have a general series like AK, from k equals 1 to infinity. So that's just the series a1 plus a2 plus a3 plus a4 and so on. We say that this series has a sum if the nth partial sums converge to a limit. So that is the sequence given by a1, a1 plus a2, a1 plus a2 plus a3. These are the nth partial sums. So we say that this series has a sum if this sequence has a limit. Here's another infinite series that has a sum. This time we'll have the series 1 over k times k plus 1, with k going from 1 to infinity. And that's equal to 1 over 1 times 2 is the first term, and then 1 over 2 times 3, then 1 over 3 times 4, 1 over 4 times 5, and so on. Now we can split up each individual term of this series. So we'll look at one term, 1 over k times k plus 1, and I can break up the numerator into k plus 1 minus k. So then I can break up the whole fraction into k plus 1 over k times k plus 1. And that's minus k over k times k plus 1. Now you can see in the first bit of this, the whole numerator cancels with some of the denominator. So that k plus 1 cancels with this k plus 1. And on this side, that k cancels with this k. So we get left with, on this side, 1 over k. And on that side we get left with minus 1 over k plus 1. So now I can substitute this back in to our original series to rewrite it. So the series 1 over k times k plus 1 from k equals 1 to infinity can be rewritten like this. Well, for the first term, k equals 1. And we've just shown that this can be written as 1 over k minus 1 over k plus 1. So since k is 1, for the first term we get 1 over 1, which is 1, minus 1 over 2. So that's the first term. We do the same for the second term. This time k is 2. So we get 1 over 2 minus 1 over 2 plus 1, which is 3. We carry on doing this, so the next one is a third minus a quarter, and so on. So from this we can work out the nth partial sum. The sum of the first n terms is 1 minus a half plus a half minus a third, all the way up to the nth term, which is 1 over n minus 1 over n plus 1. So this is the sum of the first n terms. Now, you can see that here a lot of things are cancelling. You get minus a half, plus a half, minus a third, then you would get plus a third, and so on. So overall you are left with 1 minus 1 over n plus 1, which is equal to n plus 1 over n plus 1 minus 1 over n plus 1, which is just n over n plus 1. So that was the nth partial sum. So the sequence of partial sums goes like this. It's the sequence n over n plus 1 from n equals 1 to infinity, and that goes 1 over 2, then 2/3, 3/4, 4/5, and so on. Now you can see that this sequence gets closer and closer to 1. In fact, the sequence has limit 1 So the sequence of partial sums for that last series has limit 1, and that must mean that this series has sum 1. Here's an example of a series that doesn't have a sum. We'll have the series, go from 1 to infinity again, of just 1. So that's the series that just goes 1 plus 1 plus 1, and so on forever. If we look at the sequence of partial sums for this, it just goes, well, the first one is 1, then it's 1 plus 1, which is 2, then it's 1 plus 1 plus 1, which is 3, then 4, and so on. Now this sequence certainly doesn't get closer to any number. In fact, it tends to infinity. If this happens, we say the series doesn't have a sum. You might have spotted that both the series we looked at that had sums had terms that got closer to 0. In fact, this is true always. If a series has a sum, then the terms must get closer to 0. But this doesn't work the other way round. Here's an example. We'll have the series 1 over k from k equals 1 to infinity. So that's the series 1 plus a half plus a third plus a quarter, and so on. Now, even though these terms get closer to 0, the sequence of partial sums for this tends to infinity. This series is called the Harmonic Series, and it doesn't have a sum. Now we'll have a look at two very useful infinite series. First of all, we'll look at this one. It's 1 over k minus 1 factorial from k equals 1 to infinity. So that's equal to 1 over 0 factorial, which is 1, so that's 1. Then 1 over 1 factorial, which again is 1. Then 1 over 2 factorial, which is 2. 1 over 3 factorial, which is 6, and so on. You can use your calculator to work out the nth partial sums of this. I've done this already, and the nth partial sums turn out to be, well, the first one obviously is 1, then 2, then 2.5, and then you start needing to use your calculator. So the next one is 2.6 recurring, so I'll put this down to a few decimal places. The next one is 2.708, then 3 recurring. And the next one is 2.71, then 6 recurring. And then I'll do one more, and that's 2.718, then 5 recurring. You can see that these numbers are getting very close to something just below 3. In fact, these numbers keep getting closer to e. So if you calculate the series for a large number of terms, you can work out a very good approximation for e. So this makes this series very, very useful. Here's another useful infinite series. This time we have the sum of minus 1 to the k plus 1 all times 4 over 2k minus 1. And again, k goes from 1 to infinity here. Let's work out the 4 over 2k minus 1 bit first. When k is 1, this denominator becomes 1. So this is 4 over 1, which is 4. If k is 2, the denominator is 3, so this becomes 4 over 3. The next one is 4 over 5. Then we get 4 over 7, 4 over 9, and so on. And now we just need to work out the -1 to the k plus 1 bit. If k is odd, so that's for the terms 1, 3, 5, and so on. If k is odd, then k plus 1 is even. So -1 to an even number is just 1. So all these odd terms are plus, they're positive. So I'll put pluses in front of them. But if k is even, then k plus 1 is odd, and -1 to an odd number is -1. So all these even terms have a minus before them. Again, we can use our calculators to work out what the nth partial sums of this series are. I've done this already, and the nth partial sums turn out to be, the first one's easy, it's 4. The next one is 2 2/3, so if I write that as a decimal, it's 2.6667 to a few decimal places. Then you really start to need your calculator. The next one is 3.4, then 6 recurring. The next one is 2.8952, that's all I'll do, it goes on. The next one is 3.3397, that goes on as well. Then 2.976046, and so on. And I'll do one more, that's 3.283738. Now with this sequence, it's a bit hard to spot which number it's converging to. You could probably spot it's converging to a number just above 3. In fact, it converges to pi. So if you want to calculate pi to a large number of decimal places, all you have to do is to work out a large nth partial sum of this, and that'll give you a good approximation for pi.